All right, let's go here. Done. Let's see, let me share my screen. Start the broadcast. Hopefully this works. Have to so you know how temperamental it can be. Hang out here for a moment. Oh, that looks good. What's that? What is that? Okay. You know how temperamental it can be. Okay, that's promising. Okay. Let me unplug this. Stop the broadcast. Share my screen. Let's try this again. Start the broadcast. Optimize the video. And all right, we should see a blank white screen. Start the broadcast. Optimize the video. Okay. All right, I got my confirmation. All right. So let me plug this in. So welcome YouTube, welcome scholars. What we have here, we're going to do a homework session for Calculus for Business. This is basically over questions from chapter 2, all right? So let's kind of get into it. Let's see. System. So if I go view, single page. Okay, let's try this again. Okay, there we go. So this first question comes from section 2.2, question 66, right? First, we're asked to find an equation of a line tangent to this graph at the point 0,7. So far, all of our discussions have been on finding the derivative, right? And we've said that the derivative is nothing but the slope of the tangent line at a point. So they gave us the point. So we need to find the slope of the tangent line. So in other words, take the derivative, that'll give us the slope of the tangent line. We have a point and a slope. We can find the equation of a line. All right. Okay. So let's give that a go. So let's start by finding the derivative. We got this G. Let me just get a copy. We got 7 e to the negative x. All right. And we're going to be investigating the point 0,7. Okay. So then when we go to find G prime, that's not a G. When we go to find G prime, right? So the derivative of e is itself. So we're going to have 7e to the negative x. Then we're going to say times the derivative of that power, which is, in this case, is going to be -1. So ultimately, that's going to be -7e to the negative x, okay? But then we want to find a derivative when x is 0. So we want to find G prime of 0. That's going to be 7e to the negative times 0, right? E to the 0 is a 1, so that result is -7. So what this is telling us is that the slope of our tangent line when at x equals 0 is -7. So now we have a slope. And again, I'm going to, this is our slope. And we have this point. So then we can use y equals mx plus b. Okay. So let's plug in the components. I'm going to plug in my -7. X is 0. We don't know b. Y is 7. We have everything except b. We have one equation, one unknown we can solve. Ultimately, it looks like b equals 7. Right? So then if we put it all together, the equation of our tangent line is going to be y equals -7x plus 7. Okay. I just gave this dog snacks. She ate all the snacks. Now she's like going around doing this pacing, just eating everything that she could find. It's like, man, she don't be playing around. Okay. So I think, let me see. Yeah, it should be that. So I would just try that. If it doesn't work or if it's not right, just let me know. Just stop me, and we can get to the bottom of it. But I'm confident in that result. And like basically, if we were to graph this guy and graph that equation on the line, we'd have exponential decay, and that line should graze our exponential function. Okay. All right. So then that takes us to this next question. And again, just stop me if you have questions. Or if we realize that something isn't right, because I may or may not check these, but I'm just gonna kind of go with it. What do you? Come here. What are you munching on? Open your mouth. What is this? What is this? What is that? That's your tooth. Come here. Open up. What the hell, dog? Open your mouth. Let me see. Let me see your teeth. Stop. Sorry. I'm coming. That looks good. Let me see over here. Stop. Stop. You. Ugh. She seems like she's okay, but she's definitely. I think that's her tooth. It looks like her tooth. This dog. She's wild. Get down. Get down. Oh my goodness. I think it just broke. A piece of it broke off. I think she's gonna be okay. All right. She's a lot. So here, this question comes from section 2.2, question 36. And basically we're asked to find the second derivative of w with respect to z for the given function, right? So let me see, we have w in terms of z. So we just take the derivative like normal, but instead of it being x, we do it in terms of z, okay? So we have this function, this portion that has a z and this portion that has a z. So if we're gonna take the derivative, it looks like we need to apply the product rule, right? This one looks like it has the potential to be a little nasty, but we're gonna work with it. Okay. So the product rule, first times the derivative of the second plus the second times the derivative of the first. Okay. So the first being here, not equals. But when we go to find the derivative of w with respect to z, the first derivative, the first is going to be 2z squared. The first times the derivative of the second. E to the z is its own derivative. So the first times the derivative of the second plus the second times the derivative of the first. The 2 comes down. It becomes 4z. Okay. We could factor out the e to the z, but then nothing really happens there. I would just click on the view an example and see how they submit their result. They either might submit it like this, or we could factor out a z e to the z. They might write it like this: z e to the z times 2z plus 4. Actually, we could factor out a 2 as well. So there could be a 2 here. That gets rid of this 2. Two z e to the z, 2z e to the z. So the only thing that's left in the second one looks like it's a 2. Right? They might write it like this. So you can try the first line. Okay, you can try the first line, and if that doesn't work, then try this box portion. Okay. It should be one of those two. Oh wait, no, sorry. That's just the first derivative, right? First times the second, that's a lot. Let me see, which is easier? We could do that twice. That's going to be even worse. First times the second plus the second. Okay. So this is a little bit weird, right? Let's go ahead and let's take the derivative of the derivative. So let's find the second derivative. The second derivative of w with respect to z. Okay. So I'm going to apply the product rule again. But you got to kind of catch the changes, right? So if we apply the product rule, we're going to say the first, which is this guy. I'm going to make this my first, right? The derivative of the second looks like it's just going to be a 1. Okay. So that's the first times the second plus the second, which is this guy. Now the derivative of the first, it looks like we got to apply we can actually just use our result from above, right? Because that derivative is going to be the answer, the previous answer, right? So I'm going to write it as 2z. I'm just using what we had before. Okay. Because again, when I go to take this derivative, that was the original, right? Oh no, it's not. No, it's not. No, it's not. Okay, let me take the derivative. Let me not just take that. Let's just take the derivative, right? I think we're gonna have to do the product rule again. Because right here, right? We're trying to take the derivative of this guy, but in order to take the derivative of this guy again, we have to do the product rule again, right? That's why I was saying it was weird. So that derivative first, which is this, times the derivative of the second, which is this, plus the second, which is this, times the derivative of the first, which is 2. Okay. Let's see. Let's write this in factored form. So we got this 2z e to the z. Okay. Let's see. What do we have common there? They both have e to the z and 2. So we could factor out a 2e to the z. Okay. So we're going to say plus 2e to the z. Is z plus 2 persists. 2e to the z. So we're left with a z in that first part and a 1 there. Okay. Looks like we could factor out 2e to the z. I don't know if this helps us, but I'm going to do it anyway. Looks like both of these terms both have 2e to the z. Okay. And we're going to be left with a z plus, we're going to have to simplify this down. Z plus 2 times z plus 1. I'm going to expand, combine like terms. I feel like the hardest part of this is over. 2e to the z. If we expand, z squared plus 3z plus 2. Okay. Combine like terms. 2e to the z. We got our z squared plus 4z plus 2. Okay. All right. I'm confident in this, right? So it was a little weird. We basically were multiplying 3 things, right? So we had to apply the product rule. Like instead of trying to apply the product rule 3 times, what I did was 2 of the products, I grouped them together, right? And so then I applied the product rule. And so what ended up happening was at some point within the product rule, we had to do the product rule again, right? That's essentially what happened there. So that one was a little involved. Let me kind of show the whole thing for just a moment, right? So I like that. All right, so let's just kind of go back through that one again. So this was an example on the second derivative. First, we did the first derivative. So the first times the derivative of the second plus the second times the derivative of the first, right? So I think we were good there. Okay, and then I think what we did, we kind of simplified, so we factored out. We noticed that they all had a 2z e to the z, right? 2z e to the z. So in the first term, a z was left over, 2z e to the z, and a 2 was left over in the second one, right? So then from there, we went to take the derivative of that guy. So then what I did was the first times the derivative of the second plus the second times the derivative of the first, right? So the first, you see it here, derivative of the second, you see it here, plus the second. Now, when we went to take the derivative of the first, we had to apply the product rule again. That's why I was saying it was weird. So then the first times the derivative of the second plus the second times the derivative of the first, right? Then from there, we just expand through algebra, combining like terms, and we were able to get it down to here. Okay. I am going to go with that result. I'm not going to check it. Let me think. So I'm not saying it's right or it's wrong, but the idea is there. And so I'm going to leave it up to my student that's on the session to check it, and then, oh man, I can't believe she was chewing on her tooth. Like, I'm sorry, I get distracted. I'm going to leave it up to you to check and to confirm or deny if it's not right. If it's not right, then we'll try to revisit it and like clean it up, right? But I'm going to go with it for now. Okay. So let's go into the next one. Okay. So now this one has multiple parts. So I'm going to have to hop back over to Pearson for it. This question comes from section 2.1, question 81. I think it's maybe like physical science or something. It says a cup of hot coffee is placed on a counter and allowed to cool. The temperature in degrees Celsius of the coffee T minutes after being placed on the counter is given by this function. Completes parts A through D. Okay. So that's the temperature in Celsius T minutes after being placed on the counter. So for part A, it asks us to find what was the original temperature of the coffee. So that's when our time was 0. Yeah, I kind of want to check this one, right? So if we let T be 0, right, we're going to have e to the 0, which is 1. So it looks like that the original temperature of the coffee was 81 degrees Celsius, right? We just let T be 0. So let's see if I can find this one. 2181. It's this one. 2181. We got 80 for that one, so I'm going to plug this one in. I guess we can plug in the other ones to confirm them. Settings. I want this to be off. Here, we got 80. Oh, evaluate. T of 0. All right. Okay. And the original temperature we got was 80 degrees Celsius. And it's 0, right? That's a 1. Oh, 81. Sorry. 81 degrees Celsius. Moving too fast. Okay. All right. That looks good. So then part B asks us, what is the coffee temperature after 17 minutes? So we're plugging in 17. So I am going to need my trusty dusty rusty. Let me do this right here. Okay, and let me pop this guy out. Come on. Yeah, that looks good. Okay. And let's reload and refresh. So where'd it go? Not that one. This one. So after 17 minutes, so we're gonna plug in T equals 17. So what I'm gonna do, I'm gonna go to my Y equals, and I'm gonna type 31 plus 50 e to the negative 0.019. Instead of T, I'm gonna put it as X, close parentheses, okay? That looks good. So then I'm going to call on that function that I just typed in. So on the right-hand side of my calculator, there's a button that says clear. Left of that button is a button that says VARS. I think it stands for variables. I'm going to click on that. I'm going to go to the right to go to Y variables. Then I'm going to click on number 1 for function. I'm going to click number 1 again to call that function I just typed in. So now, if T is 17 minutes, I'm just going to say F of 17. And let's see what result we get. Let's see. So we're going to evaluate T of 17. Enter. Oh, I hit 7. It's supposed to be 17. Come on. 17. Okay. And then the coffee's temperature after 17 minutes, it says type an integer or decimal rounded to 1 decimal place. So if we round to 1 decimal place, it's going to be 0.2. 67.2 degrees Celsius. 67.2 degrees Celsius. Okay, let's go on to the next part. So then it says, when will the coffee's temperature be 42 degrees Celsius, right? So they've given us the output and they want us to work backwards. Okay, let me see how much of this I can do on my calculator. We are not evaluating, we're solving for the function equal to 42. All right, so we're going to set it equal to 42 and solve. Okay, so now if we work backwards, if it's equal to 42, essentially what we're going to do, so we know we're going to have 42 minus 30, right? We will subtract 30 from both sides. Then it looks like whatever answer we get, we would say divided by 50, okay? So then we get an answer there. Then we would say the natural log of both sides. So we would say, I'm going to insert a natural log. If I need to write this out, just let me know and but this is like algebra, I guess. But if I need to write it out, just let me know. So I'm saying 42 minus 31, we get an answer. Divided by 50, we get an answer. Then I'm saying the natural log of both sides. So I'm going to say the natural log of that answer. Then, yes.
Would you write it down?
Yeah, I figured. Okay. Okay. So 42, let me get a copy. I really just want this. Which one? I mean, this is all I really need right here. Okay. So let me hit done and copy and delete. I'm gonna go here. Okay. So what we're doing is solving this equation. All right. This is what we're solving this equation. All right. Okay. So let me start by getting a copy. We got this table. Sorry. We got 31 plus 50 e to the negative 0.019 t equals 42. All right. We're solving for t. So the first maneuver, we're going to subtract 31 on both sides. Okay. And these guys are going to cancel. So then on the left, the equal sign comes down. On the left, we're going to have 50 e to the negative 0.019 t. On the right, for right now, I'm going to leave it as 42 minus 31. I'm going to leave it like that, right? So then next, if we're trying to solve for t, let's divide both sides by 50. I want you to see what I was building in the calculator. They're going to cancel. Equal sign comes down. On the left, we still have this e to the negative, this guy. And then on the right, I'm going to leave it as 42 minus 31 over 50 just for now, okay? So then, if I'm still moving things away from the t, now we want to take the natural log on both sides. That's going to cancel the e. And that's going to allow this to come out of the exponent. Okay? So this log is going to cancel this. On the left-hand side, we're going to have this negative 0.19 t. On the right, we're going to leave it as the log of 42 minus 31 over 50. Okay. Last thing, so ultimately t is going to be equal to the log of 42 minus 31 over 50, all divided by negative 0.019. Okay. That's what I was building in the calculator, right? So we got the log of 42 minus 30 over 50, okay? And then we want to say that log, you got to get your parentheses correct here. That's the biggest challenge. And then negative 0.019, right? And I'm doing this way so that we can minimize. When you're working in Pearson, the goal is to do not round until the very end. If you round early as you do your calculations, it's going to throw the final answer off. So if you're going to crunch those numbers early, you have to write out the long decimal. I prefer to do it the way that you see, where I'm just keeping it exact until the very end. But again, if you crunch those numbers early, the recommendation, write out the long decimal, and then that way, when you go to round at the end, it should behave properly. But if you start rounding early and you keep basing your calculations on rounded results, it throws off the final answer, right? Okay, so I'm going to go ahead and enter. Let's see, right here, this one. Okay, she's still munching on something. She must have got another piece of her tooth broke off or something. That's probably why she wanted some attention. That's what it was. Her tooth was bothering her. I don't know what's going on because a friend of mine is having tooth issues as well. So that's somebody lying about something. Am I lying about something? Anyway, anywho, but that's just really bizarre. It's going to be 42 degrees Celsius after it's been 75 minutes. Type an integer or decimal round to one decimal place to 75.1. Let's try 75.1 minutes. 75.1 minutes. Okay. Let's see. Solve, right? 42. Oh, I put 30. Why am I keep missing the one? Like, what is up with that? You see, and like that's why I like to do this, right? I can go back and see where did I make my mistake. Yeah, 30, 31. I don't know why I put 30. Anywho, but see, I can make the change, and then it's a lot easier for me to recover, right? Okay, let's clean it up. 79.7 minutes. Okay. All right. We put 30 instead of 31. Okay. Was that it for that one? Okay, part D. Let me get rid of this. Let me see. So then part D asks us it says, find the limit as t goes to infinity and explain what this number represents, okay? So normally exponential, we have exponential growth, but we multiply the inside by a negative that causes a horizontal flip, so we have exponential decay. That's going to stretch it vertically and then move it up by 31. Okay. So this exponential is essentially in the denominator, right? We have 50 right here. We have 50 over this exponential, right? E to some power. So as we let that power get bigger and bigger and bigger, that means the denominator is going to infinity, right? So if we have 50 divided by a really, really big number, then that term goes to 0. So the bigger that number, that denominator gets, that second term goes to 0. So as you go off further and further to the far right, then the y value is going to approach, in this case, y is going to approach 31 because that second term essentially goes to 0. All right. Let me see which one. This is the change of the coffee's temperature no, this is the number of minutes after it's been placed. No, this is the average rate of cooling. Is there another option? This is the temperature towards which the coffee's temperature decreases over time. The coffee will not fall below its temperature. Let's see. I think it's D, right? The average rate. This is not an average rate. This is the number of minutes after being placed on the counter it takes before there is no more significant change. No, this is basically talking about what happens in the long term. This is the change of the coffee's temperature as it cools over time in degrees from the time it's placed. It can go below that. Let me think about this. We got a result of, we said 31 degrees. Let's see. I guess it's room temperature. I'm thinking, let's go with D. Let me put 31 into this one. I think it's this one. Oh, come on. Let's try 31 there. Okay, right. Because again, what we're doing, we're taking the limit as t goes to infinity. So this is just in the long term. So if we just wait and wait and wait and wait and wait, what does the temperature approach? The temperature approach is 31. I was almost tempted to say A, but that didn't really make sense. This is the change. This is not the change. The result that we're getting is the temperature of the coffee when we just let it run, right? So that's why I was like A didn't make sense. And then B and C didn't make sense either. The only one that really made sense was D. That was interesting. Okay. So we got through those parts. Let's see what do we have next. Yes.
Could you explain why it's 31?
Oh, 31. Okay. Let's go here. Right here. Come on. All right. We said we want to consider as we let t go to infinity, right? I'll write it in like purple, I guess. So as we let t go to infinity, now this is the same as, let me clean this up. So now this is this, nope, I'm not filling that in. Give me just a second, sorry. Okay, this is gonna have to work, whatever it is. So this should be the same as 31 plus, now that e to the negative power, I'm gonna move it to the denominator. Right? So e to the negative is going to be the same as e to the power of 0.019 t under 50. Okay. So from there, as we let t run to infinity, this denominator goes to infinity. It gets really, really big, right? So if we have a fixed numerator over a ever expanding denominator, the bigger and bigger and bigger that denominator gets, this entire thing tends to 0. So as that denominator gets bigger and bigger and bigger, that term gets closer and closer and closer to 0. So then 31 plus 0 is 31. So that's the long and short of that one. Hopefully that's okay. So as t goes to infinity, that second term essentially goes to 0, and we're left with 31. I'll leave that note there. All right. Hopefully, here. I'm gonna rewrite it as this tends to 0 as t goes to infinity. Okay, it's a good question. All right. Let's see. Okay. Actually, switch this back. Okay. All right. So then this next question comes from section 2.4, question number 3. We're asked to find the general form of the function that satisfies this. So this is what we talked about today, where there's only one equation that's going to satisfy this form, and that's basically the exponential growth model. So it's going to take on the form P naught e to the kt. So it's going to be something like, I think that was the k. Let me think about it. Yeah. It should be something like a naught e to the 4 t. Who would think? Because I think we said that 4 was our k. So let me hop over to Pearson. See if we can submit that one. Let's see. It should be a sub 0. I'm going to click on view an example. Or C. Okay, they might be using C instead of A. Wait a minute. Okay, that's fine. Yeah, that's fine. Yeah, so just use C. Okay, so here we'll go ahead and submit it, right? So for this one, Settings. This should be off. We're gonna say C. We're gonna say CE to the power of 4t. All right, that's from the exponential growth model. Okay. So this is kind of like what we talked about today. And again, the only difference is instead of using A, it means the same thing, it's just a different label. Instead of A naught, they just put C. Okay. All right. Let's see. Can we get you to work? What does it take to get you to work? Let's see if I back up. Let's try this again. Where's it now? Let me reboot this really quickly. Yeah, it was definitely something in her mouth because after I took that out of her mouth, she calmed down. Like she went right back to sleep. I was like, man, she has her own way of communicating. It's so interesting. Let's see. I guess I thought I needed more space for that one, but that's fine. Oh, okay, here it is. That's where we left off. Okay. All right. We have a few more. So this next one, it comes from section 2.4, question 13. And it says in 2004, an art collector paid 110 million for a particular painting. The same painting sold for 27,000 in 1950. Complete parts A through D. Find an exponential growth rate K to 3 decimal places and determine the exponential growth function for which the value V of T is the painting's value in dollars 2 years after 1950. Okay, so let's see how to get to that result, right? It says exponential growth and we have 2 ordered pairs. So basically what we're gonna do is model the exponential growth model to this data, okay? I think we have some space already ready to go. So exponential growth, so for part A, we're going to be working with V of T equals, what's this? I like to call it V naught, E to the KT, right? That's just the generic exponential growth model, okay? We were also given in 1950, let me see. So if 1950 could be year 0, let's just write what we have. 1950 and 27,000. So in 1950, we have 27,000. Okay. And then we also have what, 2004. What is that? Uh-oh, what happened to my image? In 2004, 110,397,000. 110,397,000. Okay. Now, I feel like it's a good idea to just let 1950 be year 0. So I'm going to kind of rewrite all of this. And let me kind of work over here. I'm going to move this down. Okay. So let's let 1950 be year 0. So in year 0, it sold for 27,000. Okay. If it's 2004, that's what, 54 years later? So we're going to say after 54 years, it sold for 110,397,000. I need to become an artist. Like, what am I doing in my life, right? So what we want to do is find a model. We want to model this data to the exponential growth, right? So we have 2 points. We're just going to find the equation of the exponential function that passes through these 2 points. So when t is 0, the y is 27,000, right? So that means okay, we're gonna have v naught e is basically gonna be e to the power of 0, and the output is 27,000, right? So that's like our, so that basically means we're starting with 27,000, right? So then let's plug in the second piece of information. When T is 54, the Y is 110,397,000, right? So we're going to have this 27,000 times E. We still don't know K, but the time has been, what, 54 years, and the value is 110,397,000, right? We have one equation, one unknown we can solve. Let me kind of separate this stuff, right? So we have one equation, one unknown we can solve, okay? Divide both sides. I'll write it like this. First, we're going to divide both sides by 27,000. 27,000, okay? Then E to the 54K, whatever that number is, 110,397,000 over 27,000, okay? Then we're going to take the natural log of both sides. Like, you kind of got to ignore these ridiculous numbers and just kind of do the same thing. Do what you know to be right, right? So if we take the log on both sides, the log, this cancels this. That allows this to come down. On the left, we have the 54K. On the right, we just have, I'm just leaving it. Natural log 110,397,000 over 27. Hopefully I'm not missing any digits or anything like that, okay? We're gonna divide both sides by 54, okay? And then ultimately our K is gonna be this 110,397,000, 27,000, log of that, all over 54, right? That's the exact result. For part A, find an exponential, find K. And then, okay, let's find that K. And we found V naught, and we're about to find K, so then we can model it, right? So V naught is right here. This is what we got for V naught. And then for K, we're gonna trusty dusty rusty. So let's clear. We got the natural log 110,397,123 divided by 27,123. Okay, that's the log. We want to say that log divided by 54. Okay, we get 0.154 approximately. Right, so K is approximately 0.154. Okay, so we got our K, we got our V naught. So then the value of the painting, V naught, we got 27,000 times E to the K, 0.154 T. Nope. Okay. Let's go here. Like this, all right? Style, so 6. Let's copy, okay? I think we have the result already. 27e to the 0.154, you see it there. So that's the backstory there. Then it says predict the value of the painting in 2024. So we did it based on what? 2004. So 20 years later, so then 74. So then basically we plug in 74 into our model and we should get that result. Okay. So our model, let's go put it here. We got this 27,123 times E to the power of 0.154 x. Then I'm gonna just call on that function. Can I just back up some more? No? Do one more. There it is. So I think we said 74, right? When after 74 years. So all I'm doing is plugging in 74 into the model that we created. We should get, what is that? 1,000 million, 2.4 billion. Let's see if it works. 2,402,000, round to the nearest million, right? So it says round to the nearest million. Okay. So you just have to round up. It says estimate the rate of change of the painting's value in 2024.
Professor,
Yes.
are you round to the nearest million?
So this 2.4 is in billions. So the millions place is the two, not is the two, right? It goes 2402. Behind that two is a zero, so that means it stays as two. Is that okay?
You said what?
Can I zoom in? So here, let's do this. So in the calculator, we got 2,402,050,59,052. All right, that's what we got in the calculator. The millions place is right here. So if this is the millions place, that means we have to look at the zero. Because this is a zero, that tells us that this stays as a two. If this were like a 5 or a 6, anything larger than 5, then this would become a 3. All right. So that's, yeah, you just have to focus on this guy. The number behind it tells us that we stay the same. So then it stays as 2. So that's where the 2,402,000,000 came from. The rate of change of the painting's value in 2024. So we can apply that theorem that we kind of did today, that we were working on earlier, where we just take the previous result times the rate, right? The K in the rate is the 0.154. So if we take that answer and we say times 0.154, that's where the 370 million comes from, right? It says round to the nearest million. So again, for part C, we got a result of, it looks like it's 369,917,094.1. Again, if it says round to the nearest million, the millions place, let me see, 1,000 is right here with the 9. So behind the 9 is another 9, which is larger than 5. So that means this rounds up. So the next number up is going to be 370 million. And that's where this 370 came from. All right. This one tells us to round up. So that's where that came from. How long after 1950 would the value of the painting be $6 billion? Okay. So what we would do is set our model equal to 6 billion. We would set our model equal to 6 billion and then solve. So I think we need to write out the 6 billion, divide, take the log. All right, I'm just gonna kind of crunch the number here. So let me see, that's 1, 2, 3, that's 1,000. 1, 2, 3 is million. 1, 2, 3 is billion. I'm gonna say minus 27, 1, 2, no, not minus. I'm gonna say divided by 27, 1, 2, 3, divided by, come on, 27,000. Then I'm going to insert, there it is. Insert my natural log, because I'm taking the log of that. Then that log, I want to say divided, but it's kind of a repeat of what we had before. divided by 0.154, just with the slight change. Divided by 0.154. Okay, and we should get an 80. Let's see, what are we missing? 6 billion. How long? Let me go back. Let me see, 6 billion. Let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9. Let me try to redo this. Let me recall. Let me redo this number. 6, 1, 2, 3 is 1,000. 2, 3 is a million. 1, 2, 3 is a billion. Divided by 27,000. Okay. We take, oh, I see what's going on. I'm missing a parentheses. That divided by that, yeah, right here. I'm missing a parentheses right here. Okay. All right, I think that'll fix it. So then we should get 80. All right, we were just missing a parentheses. So with that missing parentheses, it was putting that 0.154 into the log where that's supposed to be outside the log. So then we get our 80, right? I just didn't write it out, but we did one similar. It's just different numbers. If I need to write it out, I will just X and write it out. Okay. But again, to recap that one, we set our model equal to 80, right? So our model is here. If we set that equal to 80, wait a minute, not that one. Sorry. How long after 1950 will it be 6 billion? So if we wanted to be 6 billion, we set our model equal to 6 billion, divided both sides by 27,000, took the log of both sides, and then divided that log by 0.154, and that's where the 80 came from. Okay. Let me see how many more. We might have 2 more. This might be the last one. I think that's the last one. Yeah. Okay, this is the last one because I'm fading. Okay. So this question comes from section 2.4, question 35, and let's read it. So it says that pharmaceutical firms invest significant money in testing any new medication. Now I'm thinking about COVID and how they didn't test it thoroughly like that, like they did everything else. Like that's such a scam, boy. I tell you. Don't get me started on all of that. Like don't get me started. Hopefully I don't get flagged because I just realized it's like there's a whole conspiracy behind all this stuff. But anyway, pharmaceutical firms invest significant money in testing any new medication. After the drug is approved for use, it still takes time for physicians to fully accept and start prescribing the medication. The acceptance by physicians approaches a limiting value of 100% or 1 after a time t in months. Suppose that the percentage P of physicians prescribing a new cancer medication is approximated by this equation below. Complete parts A through D. Okay, so for part A, it says what percent of the doctors are prescribing medication after 12 months? This T is in months, right? So we just plug in 12. Okay. So what I'm going to do, I'm going to go to my y equals and type in this function. 100 parentheses 1 minus e, which is here, second log, 1 minus e to the power of a negative 0.36x. Okay, close off my exponent and close out the other set of parentheses, okay? So then I want to call on that function. Okay, there it is. And we said after, was it 12 months? 12 months, right? So we basically plug 12 into our function. We should get 98.7%, right? Round to the nearest 10. So then we're asked to find P prime of 12. So we need to take the derivative. Okay, and let's take some notes here. So then let me start by getting a copy. We got this P of t 100, 1 minus e to the negative 0.36t. Okay. I'm just going to move that right here. So then when we go to find p prime, we're basically saying dy by dx, or this, the derivative with respect to t of the right hand side, but this 100 could just, you can just move it in front of the derivative, right? So it's really just the derivative of this guy. Okay. So then that's going to be 100 times the derivative of 1 is 0. The derivative of e is itself. So first let's go ahead and write the e to the negative 0.36t. But then we have to say times the derivative of the power. So the derivative of the power is negative 0.36. Okay, let's simplify this guy. So double negative is positive. If we multiply by 100, we're going to get 36 e to the negative 0.36t. Okay. So then from there, we plug in 12. So then p prime of 12 is 36 e to the negative 0.36 times 12. Right? And then that, at that point, it's a calculator problem. 36 times e negative 0.36 times 12. Okay. Let's see. It looks like you put negative. It says then round to the nearest 10th. So the nearest 10th, is that right? 10th, right? So that's one decimal place. So it looks like it's 0.5, positive 0.5. Okay, let's copy for the Pearson for that one. So that one is 24.35. 24.35. Let's see. I think it's like this one. There it is. Okay. So this one looks like it's still doing this thing. Okay. And it's sent off. I don't know why it keeps popping up. I think we got 0.5, a positive 0.5. So let's just put 0.5. There's 10. Okay. Was that it? Oh, no, that was A. Let's keep going. So then what's the interpretation? This is the rate of change. Let me see. This P. Yes.
How'd you get a 0.5?
Okay. Here. All right. When we crunch that number, we got this positive 0.478, yada yada, all that stuff. But then the instructions say to round to the nearest 10th. So here, let me write it like this. So in the calculator, we got a result of, we're going to say that this is approximately, we got this 47879, yada yada yada. That's enough. But it says round to the nearest 10th. So the 10th position is this 4 right here, right? So if we're gonna round to one decimal place, we got to look at the number behind the 4. That 7 tells us to round up. So that's where the 0.5 came from. So this, if we round to one decimal place, that's where the 0.5 came from.
Okay, thank you.
Yep. So then, let's see. So P prime, that's going to be the rate of change. Let me see. Suppose that the percentage of physicians prescribing new medication So this is going to be the rate of change of the percent of physicians prescribing this medication. That feels like a tongue twister, right? At 12 months, the percent of doctors at 12 months, 0.05% of the doctors are prescribing. No. At 12 months, percent of the doctors who are prescribing medication is increasing by, it's a rate of change, right? 0.5% per, or T, let me see, what is T? T months, right? I'm thinking D. It's not decreasing. B and C, that's not what it is. It is increasing, right? So we're gonna go with D. Okay. Let's keep going. Sketch the graph. Let me think about it. So for exponential, but then we multiply the inside by a negative, so that flipped it horizontal. So now we have exponential decay. We multiply the out. So instead of exponential decay, it's this weird upside down exponential decay. Okay, that's fine. And then we stretched it. So I'm thinking D. All right, let's go with D. So I was basically using transformations from college algebra. You could also choose several values of T, find the corresponding Y, right? D, all right? Because again, we said that over time, more physicians prescribe this until they reach 100%, right? And this is the only one that shows more prescriptions, more physicians prescribing this prescription until it gets to 100, right? That's the only one that kind of matches the narrative. Okay. Now my dog is snoring. I don't even know if you guys can hear her or not, but she's snoring like a grown man. She's a little chihuahua. this little being has like so much personality. It's like it's not even funny. Okay. I think that was it. That was
Professor.
it. All right. Did you want to ask any more questions, or you okay? All right. So that was So that was
graph of the original function or the
say it one more time.
is that the graph of the original function?
Let's see here. Yeah, that model, right? It says sketch a graph of the function. So that P of T is just a graph of, like, it's yes, of the original.
Okay.
Yeah. Okay, I think I am spent. We're gonna have to try this. So we can do this again on Wednesday. I don't mind doing this. I am kind of spent right now. So if you have more, you can either email me or we can do this another session like this on our Wednesday. Okay. All right. Did you have any other burning questions about anything we talked about before we go our separate ways? Okay. So if there aren't any burning questions, we're going to go ahead and end the session here. From one beautiful mind to another. Enjoy the rest of your day. That was awesome. Thanks. Take care. Peace.
Bye, Professor.